Hello, my name is Brandon Mitchell,
I'm Connor Ebeyer.
And I'm Elijah Ramsey.
and this is our presentation on the tragic engineering disaster of the New Orleans Hard Rock Hotel project, prepared for Dr. Prabhu, Professor of Engineering Materials at Louisiana Tech. First, it's important to establish some background on the construction project. The Hard Rock Hotel of New Orleans construction project was originally known as 1031 Canal. It was being constructed on 1031 Canal Street in the central business district of New Orleans, Louisiana. The project had been in development as the Hard Rock Hotel for over a year and a half and was seeing great progress until an unfortunate tragedy struck in October of 2019. What happened? The floors of the Hard Rock Hotel construction project were made up of concrete and a corrugated metal decking. 8 days prior to October 12, 2019, however, the workers had placed the last roof they would place of the project. Because of an error in the decking, the building collapsed under its own weight, killing 3 workers and injuring dozens more. Here is a video of the collapse of the Hard Rock Hotel project. The top floor supports buckled under the weight of the concrete used to make the floor. This stress transitioned to other nearby support beams and resulted in a massive ripple of support failures. This ultimately resulted in half the top of the building collapsing upon the lower floors, and part of the constructed project even falling onto 1031 Canal Street.
Why did it fail? The building collapsed due to insufficient support for the upper floors of the building. Workers called for higher gauge decking in order to save money. Higher gauge decking would mean the metal decking used to support the concrete would be a lot thinner and thus would be unable to support the full weight of the concrete they planned to use on the project. In order to make this kind of decking work, you would need to reduce the distance between each support beam and add more to increase the full load they could possibly hold. Unfortunately, this change was never made, and plans proceeded to use the same span for support beams as originally planned, with the thinner and therefore weaker metal decking to hold up the concrete. How could this disaster have been prevented? The main cause of the collapse was due to the support beams on the 16th floor being too small to support the floors above it. The original design used W10 by 49 steel I-beams, which would have been able to support the structure soundly. However, the owner of the hotel wanted the ceilings to be taller than they were, and the easiest way that the engineers could find to do this was to reduce the size of the beams on the ceiling to W6 by 20, granting an additional 4 inches of the height. However, the engineers did not redo their calculations for the structural integrity, including the new beam sizes, or if they did not do their calculations correctly because the beams were highly overstressed, having only 2/5 of the original tensile strength and even less of the original structural strength. The decking that was used for the floors of the building also caused way too much weight because they were made of concrete, which is a very heavy material. If the engineers used a different, lighter material, even just for the floors above 16, the new W10 by 20 beams might have been able to support the weight. The decking itself was also a problem, as the metal decking supporting the concrete was not was not up to city limits and was a main component of adding excessive flexural stress to the supports.
To understand how having larger supports could have saved the structural integrity of the hotel, you first need to understand how the stress on the supports is applied. Combinations of forces are applied compoundingly at a point if there is no counteracting forces elsewhere, meaning that the supports on the 16th floor had to support not only their own floor, but also the weights of all the floors above them. Stress also increases largely as the cross-sectional area decreases, so using the smaller beams causes them to experience much more stress than the larger beams, as their cross-sectional area is much less. This relationship is exponential. For example, a beam with a radius of 2 inches will experience 4 times the stress of a 4-inch radius beam. Stress concentration also occurs across the beams at any point where the beam's shape changes, like the corners or sharp edges of the beam. The moment of force of the beam is also at its maximum in the middle of the beam, because all of the weight from the sides of the beam compounds onto the middle where there is no support. That means that a small amount of force could cause a beam to bend if it is long enough. All of these beams are made of structural steel. To understand how the engineers calculated what beams to use and how the new beams could not meet those calculations, we need to understand how structural steel is made and its properties. The most common way of making structural steel is called basic oxygen steelmaking. This process starts with heating up a high carbon concentration iron solution, usually around 4% carbon, until it melts to a molten state. Then, as we see in the video, a tube is inserted into the mixture that blows oxygen into the iron-carbon mixture. This oxygen will bond with the carbon and form CO2 and other substances that can be filtered out of the steel solution. They do this until there is about 0.04% carbon left, and gather the somewhat pure solution of steel, which is much more ductile than in its original state. To further purify the steel, basic materials like dolomite and lime can be added as well, which can remove substances like phosphorus from the steel and can also prevent over-oxidation during the process. In the end, steel is usually mostly pure and they can shape the ductile metal into the I-beam for whatever purposes they need. The tensile yield strength of structural steel is 62 ksi, and the modulus of elasticity is 29,000 ksi, which is relatively high as far as metals go. But if you notice, both of these units are measured in per square inch, which means they're dependent on the area of whatever shape they are molded into. So even with very tough steel, if the cross-sectional area of the beams are too small, they will still break. Now let's take a look at the types of beams they used for the Hard Rock Hotel. They used W10 by 49 beams originally, then switched to the W6 by 20 beams after they made the decision to increase the height of the ceilings. Here I have a table of the key differences in the values of the two types of beams, and as you can see from the table, the W10 by 49 beams have much more area, which leads to much more tensile strength and flexural strength. Some engineers who were assigned to figure out why the hotel collapsed came to the conclusion that it collapsed first through one of the horizontal beams bending. So let's take a look at the bottom values on the table. This basically is saying that if you have a force pushing on the beam, then the amount of flexural stress that the W10-49 beam experiences will be divided by a larger number than the W6 by 20 beam. It actually experiences about 4 times less flexural stress than the W6 by 20 beam, and has about 2.5 times more tensile yield strength. When the engineers swapped over to the smaller beams, they must not have noticed these drastic changes in the stress capacities, because if they had, they would have changed the beams back to the larger ones. In conclusion, the Hard Rock Hotel collapse was a disaster that killed 3 workers and injured many others on October 2019 in New Orleans. The engineering firm in charge of building the hotel is facing numerous lawsuits for neglecting to foresee the disaster and to do anything about it. The main cause of the collapse was the support beams on the 16th floor being far too small after the owner of the hotel wanted to change the height of the ceiling a little bit taller. The smaller support beams could not handle the weight and were highly overstressed, leading to a collapse of the entire structure as it was nearing completion. The main and obvious way to prevent this disaster would be to increase the size of the supports on the 16th floor back to what they were when the engineers did the initial stress calculations. Thank you for watching this video, and we hope you enjoy it.